So let's look at this stochastic process. So we have two processes actually, x of t and y of t, or Whiteson stationary stochastic processes. So the problem is, of course, this is a function of time, and so the z of t is a stochastic process. We want to find out about its properties. So x of t, let's say, has an autocorrelation function rxx tau, and with the power spectrum sxx omega, because it is given to be Whiteson stationary. Same thing, let's say, with y of t. Y of t is, of course, also Whiteson stationary, and ryy, and I'm going to assume that x of t and y of t are also, let's say, independent. So this is also Whiteson stationary, with whose Fourier transform of the autocorrelation gives the power spectrum of y of t. So let's look at the expected value of z of t. So I'm going to use because there is too many things going on, we can use the conditional formula for this. So expected value of z of t of conditioned on y of t. So this is going to be expected value of x of y of t conditioned on y of t. So let's say these are zero mean. So condition, since x of t and y of t are both the zero mean, so once you condition it, the expected value of this is going to be zero mean, and so z of t is mean is 0. And if you look at the autocorrelation function of z of t, this is expected value of zt1 multiplied by zt2. But again, I'm going to use the conditional formula. So this is the expected value of x of yt1 multiplied by x of yt2 conditioned on yt1 and yt2. But remember, once yt1 and yt2 are conditioned, this is simply becomes expected value of some tau1 multiplied by it's of the form expected value of tau2. But x of t itself is Whiteson stationary, so this becomes inside quantity becomes rxx of the difference of the indices. The difference being now yt1 minus yt2. And of course, this expectation is now with respect to this new random variable yt1 minus yt2. But remember, on the other hand, rxx tau and its a power spectrum are Fourier transforms, or in other words, rxx tau can be written as 1 over 2 pi minus infinity to plus infinity sxx omega e raised to j omega tau d omega. So we can use that expression here. So this can be written as, the inside expression can be written as 1 over 2 pi minus infinity to plus infinity sxx omega e raised to j omega tau. Tau is being played by now yt1 minus yt2 d omega. So of course this expected value is on this. So consequently this now reads the RCC, which is all this. Or 1 over 2 pi minus infinity to plus infinity sxx omega e to the power j omega of let's say some random variable y, which is this one. I'm going to call this for now as y d omega. But notice that this is the characteristic function of this random variable y. So we could write this as minus infinity to plus infinity sxx omega a characteristic function of y evaluated at omega d omega. But this characteristic function could depend on T1 and T2 in general, unless there are other conditions are given. Of course, we know that we can easily find the mean and variance of y. For example, mean of y is going to be 0 because, and the variance of y is expected value of y squared, which is expected value of yt1 minus yt2 squared. So that's going to be expected value of y squared t1 plus expected value of y squared t2 minus 2 times the expected value of yt1 yt2. But y of t itself is Whiteson stationary, so we could write this as ryy0 2 times minus 2 ryy, let's say t1 minus t2, and I'm going to call this to be tau. So this is 2 times ryy0 minus ryy tau, which is positive because ryy tau is always less than 0. So that's the first and second moments, but unfortunately other moments could depend on T1 and T2 separately, unless we make further assumptions. So suppose I assume that y of t, so this is as far as it would go in terms of the autocorrelation function of z of t. But so in general, the answer is the z of t need not be, if it is just this, z of t need not be stationary, Whiteson stationary, because this quantity could depend on the higher order moments, unless y of t is Gaussian. So let's say y of t is a Gaussian process. Then we know that y is also Gaussian with the 0 mean and variance 2 times ryy 0 minus ryy tau. So I'm going to call this sigma squared. And at that time, the characteristic function of y, this is a classic expression, e raised to minus half omega squared sigma y squared. And if I substitute for sigma y squared, this is going to be e raised to minus omega squared multiplied by ryy0 minus ryy tau. So we have, to summarize, so in this case it is pretty clear. If you look here, this expression only involves tau. So let me write it here. So that way we get, or we can say that z of t is also Whiteson stationary, and it is given by sxx omega e to the power minus omega squared ryy 0 minus ryy tau d omega. So clearly this is a function of only tau, and consequently z of t is Whiteson stationary. And we can, using Parseval's relation, if you want, we can also write this as, so the inverse transform of this is Rxx tau, and the inverse, this is the inverse transform of this again has the same shape, so that's going to be so this is in the denominator. dt. So either way, either this expression, so this is multiplication here. So the inverse transform of this is this, inverse transform of the Gaussian shape is Gaussian shape, except the variance will come in the denominator. And so this will, I mean, this is as far as the integration is concerned, tau is a constant. So here the variable of integration is omega. The same expression expressed in time domain, you can also, so either way you notice that this is a function of tau, and consequently the z of t is a Whiteson stationary process, provided the y of t is a Gaussian process. And notice that for this conditional thing to go through, you also need the two processes to be independent, which I already assumed here. So these two processes are zero mean independent Whiteson stationary stochastic processes. Then the autocorrelation function of z of t is in general has this form, and it is not Whiteson stationary, unless we make the extra assumption that z of t is y of t is a Gaussian process, then the z of t is also a Gaussian process, and z of t is also a Whiteson stationary process, and its autocorrelation function can be expressed in terms of either the autocorrelation functions of x and y, or in terms of the respective power spectrum.